All right. So this is the virtual process control system. In the demo version, we don't have all the modules, but we have what we need to do our experiment now. So this is the process tank. Here we have the sump tank. There is a schematic of the process here, diagram. Here we have a pump and a flow meter and a motorized valve, PAD module, on-off module, as you can see. And on the other side, we have a voltage source, level conditioning signal module. And let's start working with it. So if I am a student, then I could question myself, what can I do here? And we have only these 5 buttons here. If I click this first button here, then I can see the topics covered by this Marcin. These topics here are the topics of content in experiment that are available also in the manual of the equipment. So if I'm going to study level control and I click here, then I have a topic content, which brings me a lot of theory about what I'm going to study. This is mainly focused on the PAD, which is the experiment we are going to run now. And then I have this experiment here to run. So as I said, in the full version, it goes from signal conditioning through on-off and goes over and over up to PAD. But since we are in the demo, then it brings only PAD, which is an interesting experiment to be done. So if I click the experiment, then I have instructions on the experiment, and it tells me that I'm going to work on it in 3 steps: assembly, wiring, and simulation. So I'm going to start the assembly. And here I have the instructions on what I need to assemble and how I need to assemble it. So I just need to follow the instructions here by assembling the modules here. So voltage supply, signal conditioning module, PID controller, and pump driver. As you can see, when you place the mouse over the equipment, then you can see the name of it also. So it helps, especially when you are far away from it. Okay, so I finished my assembly. I'm going to do something wrong here just to show you a feature. I'm going to leave it out. And I'm going to try to deliver. So I am the student. I believe I did this step correctly. I'm going to ask this Marcin to check if it's okay. So by clicking here, I receive a report saying that these green items here are properly assembled, but this white one is missing, which is the pump driver that I left here. I'm going to get the on-off controller by mistake and place it here and try to check again. And then it tells me that this is missing and this is unnecessary. So I'm going to get it out and put the pump driver here. And please allow me to go on. Oops, there is still a problem because the correct position is here. So everything here was built to help and guide the student. So let's think about the student who is working home, and he will find here all the guidance to go through the experiments and finish them with success. So now we're on the wiring part. What do I need to do? I need to get the set point signals, the level signals, put it into a PID controller, get the error to a PID controller, then get the output and bring to the signal condition to the driver module. So here we have detailed instructions on how to do all that. And let's go do it. So as you can see here, for each equipment that we can interface with the electronic modules, we have these lines here pointing to the connections. So here is the level. I'm going to get them and connect to the signal conditioning. And then we need to get the output and get put here. Then we need to connect the set points. Okay. Now I'm going to get the P, I, and D outputs. Then I get the output from the controller to the driver, the pump, and then I need to connect the pump, which is this one here. Okay, so I have wired everything, and now you understand why we have even the position suggested to the student, because it makes it a lot easier to connect and to see the overall thing. So I believe I finished it properly. I'm going to take one wire out just to leave a mistake and show you what happens. Check wiring, and what does it tell me? Everything is okay. There is a wire missing, which is between the pump and the pump driver. It's the one that I took out. I'm going to make a run connection and try to check. So run connection, connection missing. I'm going to delete that and make the correct connection again. Here, okay, so, all right, I am authorized to go to the measurement and simulation, which is the fun part on all that, or at least the more fun. So here we have the instructions to simulate. It tells me to get all the set points on 0, close the valves, and increase the set point. So let's play with our plant. So here we have the power source, okay? Here we have the tank, and here we have the pump. What I want to do is I want this PID controller to control the level here. So let's see it happening. I'm going to set a level here. By now we have defined that each 1 voltage here is equal to 1 centimeter there. So I'm going to place it on 5.2. And nothing is happening here. And why is that? It's because I have no gain in the controller. So I'm going to bring some proportional gain here. And now it's rising. I'm going to open a little bit the drain valve. So I have a disturbance, and the controller is going to properly work. I need to get to 5.2, right? So it's rising here. Close a little. Okay, just a little bit open. Okay, but since we have only the proportional gain, then of course we are not going to reach the set point in this condition. So I'm going to increase the integral gain here. And now the controller is going to be able to reach the set point that we established. So it passed a little bit, then it goes down. It's going to stop somewhere near 5.2. See, the controller is doing his work, trying to get the process variable into the set point where we placed it. So if we change the set point, then the controller is going to try, I put here on 6, put more, 7.6. So now the controller is going to try to bring the level to 7.6. And now past the overshoot, and now controller is going to reach the target. Okay, so this is mainly what the solution does. How does it work? The student opens it, access a topic, then by accessing the topic, the student has access to content and experiments. Say something, Helmi. Oh, we have 10 minutes, right?
No, no, Dennis, nothing. You can go on, please.
Okay, I'll make it quick since we have 10 minutes only for the next webinar.
You are in good time anyhow.
Okay, so just making a brief review, the solution is not only a simulator. It brings the topics and it brings the guidance. When we finish this experiment, then we need to deliver it by filling a form with the proportional, integral, and derivative gains. And so when we get to the optimal solution and we type it into the solution here, then we'll be able to go to the next experiment. Before that, you can't go. So the student goes experiment by experiment when he or she finishes the previous one properly. So here in the presentation, continuing it, we have this Marcin family. The first ones were the virtual environments to teach automation. Then we talked about the Open Lab Marcin, and now we have the virtual process control Marcin, and the family is going to grow in the next months. De Lorenzo brings a new concept with this because, as you could see, it's not only a simulator, it's a smart simulator. And why is that so? It's because it guides the student and the professor is able to follow the student's progress remotely. And why is that important? It's because you may have heard this word many times, asynchronous. And the thing is, our solution guides the student through the process when the student is not in front of the professor. The platform validates that the experiment was properly done. You saw that step by step, and the professor may follow the student's progress. So this is what you saw. We accessed level control. There were a few experiments over there. And then we had to go through assembly, wiring, and simulation to be able to go to the next ones. And then that's how it goes from one to one. As I said, you can see the progress, and you can access it with the ways to access it, to authorize access, can be in three ways: through USB dongle, through internet authentication if you have good internet, if you don't have USB dongles, and if you want to have a local server on the school, we can install it. I'm going to stop the presentation here.
So it is our webinar, as I told before, webinar number 10. We have started, I think, in March, and now we are on July on the number 10 webinar regarding Open Lab and Smart Simulator. We have put it also Open Lab because, as I told before, it is based on configuration Open Lab, but it is a general also software simulator, smart simulator. So as you know, I repeat just a little bit something, just if somebody wasn't with us last times. The Lorenzo machines, you can find them in all the laboratories in little bit. Okay. Of several of the most prestigious technical education in all worldwide. So this reflects more than 50 years of experience proposing quality products and complete training solutions adapted to the needs of the industry. And most of them, you know that our electric machines lab are very strong labs because De Lorenzo has founded exactly on civil installation and then on electric machine and so on. So just to give you an idea about the electrical machines portfolio, as you see, we have different power labs. We have low voltage lab, 300-watt lab, and 1.1 kilowatt lab. The 300-watt lab, we call it Euro lab, and 1.1 kilowatt lab, we call it Unilab. And on low voltage, we have two configuration in the electrical machine study. We have open lab automatic and open lab semi-automatic. So I focus today on open lab semi-automatic because the smart simulator software is based just in most of application on semi-automatic, or we call it also manual open lab system. So also our, as you know, our systems, they are wants to continue De Lorenzo representing a strong qualified reference point in the educational panorama by increasing its training proposal. So we use the new information technology tools and media, and we improve also the experiment manuals offering to the technical and vocational institutes and also for universities worldwide more and more efficient and effective products. So De Lorenzo offers a wide range of products for the study of electric machines, both AC and DC, and their integration also in industrial application and automated system. Our OpenLab system, as you know, it is a dissectable machines. So here it is a very detailed composition, and the student can assemble different types of motors and generators in direct current and alternating current in order to understand construction techniques before carrying out practical tests to determine their operating characteristics. And it is an open electrical machine laboratory where rotor windings, stator windings, and brushes are completely exposed, and where almost all electrical machines can be studied. So developing this compact system allow to assemble AC and DC electrical machines, leaving the student the possibility of a personal critical realization with the aim of a real knowledge of the various constructive techniques. So the main basic unit can be assembled and disassembled very easily, and the whole system allows performing a large number of experiments for both motors and generators. It is supplied at low voltage in order to prevent risk of accidents. The areas of study cover, this system cover all the area study of electrical machine. I mean, principle, you can study also principle of electromagnetism, without any, by supplying the stator, you can verify also the magnetic and electric fields. You can study the DC motors in all the configurations, and also DC generators in all the configurations. I mean, separate, shunt, series, and compound. And also, this is the part of DC. Regarding the part of AC machine, you have three-phase slip ring, squirrel cage, single-phase repulsion, and capacitor motors. In AC machine, you can study also the Dahlander connection, and you can perform all the experiments regarding the synchronous three-phase motor as alternator or as motor, and study it as universal motor. As I said before, it is dissectable machine. There is power supply, electrical measurement modules, mechanical measurement modules, loads and rheostat, electromagnetic brake to simulate a load with load cell, and many other accessories like adapter brackets, locking rotating device, parallel board, pole changing module, star delta starter, and starting and synchronization module. With it, we have also this very important software using the electrical and mechanical measurement module. We can monitor all the parameters on serial communication using Modbus RTU protocol. You can also plot all the operating curves, acquiring all the data, and you can make also, we can supply also a simulation, dedicated simulation software. So to study from the beginning at the end, you can dimension all your machine, and you can test it before real application. This is just an experiment model, the more example extracted from the manual. As you see, it is, for example, this one, three-phase squirrel cage motor, 2 poles with configuration delta, and 24 volt as a voltage supply. We have this diagram connection. We have the procedure step by step what to do in the after performing the wiring connection, and then the formula, necessary formula to fill the table, for example, in this case, with other data not available in the modules. And at the end, you can plot your curves, and you can compare also with real curves, separated real curves, just to have an idea if the machine is under test, is running correctly. So this is the part that we have dedicated just to refresh our Open Lab system. And now this DL Open Lab trainer goes digital. It means we have developed a smart simulator software. So to make by your own all the experiments listed in our manuals, it's about 45 experiments, doing on software mode, so without any hardware. And my colleague Dennis, in a few seconds, will start to explain you this DL. The code of this system is DL Open Lab Smart Simulator Electric Machines. So this is a laboratory for the study of electrical machine in smart simulator version. You can do until 45 experiments, and the great tool for remote learning. That just was what we have talked before. So I leave you now with my colleague Dennis with his presentation and also with demonstration of the software.
Good morning, everyone. Thank you, Helmi.
Thank you. I stop my share. Yes. Okay. Just go on.
Can you see mine now?
Yes.
All right. So good morning and good afternoon to everyone. This presentation today is part of the Lorenzo's initiatives in order to help institutions to keep education up and running. So the questions we are helping to answer is how can we provide practical skills on distance learning? We already had a chat about how to do that in the automation field, and today we are going to talk about that on the electric machines field. So how can we help the institutions? What we can do now is become digital. So we have built a virtual open lab, a digital one, so the professors and students can have the same experience or very alike experience in the digital world. The software is not just a simulator, it's a smart sim. We'll get to that in a few slides. But the thing is, it's got the contents that the student needs to learn. And when you access a content, there is all the theoretical aspects of it. Then the student is guided through the process of assembling the electric machine. So he's got all the instructions to assemble, and he's going to drag and drop what he needs to that experiment. After doing that, then the student delivers his assembly. This is a very important feature in this the software, because the software verifies automatically if the student did everything he needed to do before letting him go to the next step. So after assembling everything, the step is to connect things, to wire. So he's got all the instructions, schemes, and images, so he can perform all the wiring. And then again, when everything is finished, he may deliver the wiring. We will see that live. I'm not going to take long on the presentation. So here, I just wanted to show you one experiment very quickly. So it's interaction, changing set point here. Okay. So what's important here, besides the fact that we have a virtual software? We had this, we took care for not developing a simple simulator that would give the professor a lot of work to use. So we wanted to build a tool to teach electric machines, a tool that provides a very unique experience to the student and that saves time and helps the professor on the learning process. So it's not a simple simulator, it's a smart simulator. And why is it smart? Because besides the virtual environment that is typical in each simulator, it's got the topics, the contents. The professor can track the student progress, and it's got some help and instructions not only on how to use the software, but how to learn with it. And why is that so important? Because the students can work asynchronously. There are some terms that are coming to our daily lives, and two of them are synchronous and asynchronous things. So I am a professor like some of you guys here, and I understand the challenge we are facing. And one of them is you have a group of several students, each one has a different, lives in a different context. So what the Smart Sim helps you to do is the Smart Sim guides the students through the process. So each student can work on his or her own rhythm in the time he or she got available. And the platform validates every experiment. So that means that mimicking what happens in the classroom, when the student does an experiment, he would call a professor or instructor or technician or a colleague to say, hey, look at here, is it okay? What do you think? So the platform, the solution does it for you. And the professor may follow the student's progress. We'll see how that happens. So the student, giving you a quick view, the student logs into the software. He sees the topics and contents. He's guided through instructions. Then he works on assembly, connections, and experiment. As I said, as Helmi said, the software covers from basic ideas through induction motor up to direct current generators in detail. There are 45 experiments to be run. And when we get one topic, we have several experiments. I'm getting 4 here just for an example. So the student needs to assemble the machine, make the connections, and run the measurements. In the end of each step, there is a validation feature to verify if the student did it properly. And just when the student finished this, he or she is allowed to go to the next experiment, and so and so. And by finishing all experiments in one topic, the student is allowed to go to the next topic. So it's very much like what we do in the classroom with the additional feature that the student is guided automatically. So the point is, every time the student finishes a topic, then the software records his progress, and that's how the professor can know exactly in which point the student is. So the student goes into this process every time, in every experiment, he's got instructions, works on it, job asks for validation. Is it okay? Next experiment. It's not, he's got some feedbacks to identify where the problem is. At any time, the professor can verify the progress of the student, and has got a detailed report on what the student did and at what time. And to finish the presentation, I'd like to talk about the access methods. This software is very flexible on this point, because if you don't have an internet connection in your area, or it's not good, and it happens in some parts of some countries, then we can provide a USB dongle. The good part on it is you don't depend on the internet, but the bad part is you can't lose the dongle. If you do, you need to require a new one from us. If you had good internet coverage on the school and on the surroundings, so you can use internet authentication. So it means the student can log in with email and password from anywhere in the school or home or in the bus, anywhere. He just needs to have a laptop. The problem on it is it depends on the internet. Without internet, it doesn't work. And if the school doesn't have a good internet, but doesn't want to use a USB dongle, for example, we can provide a local server, a PC that's going to be installed in the institution and is going to handle the authentication. So the student will be able to log into the application anywhere in the school by using email and password. And the problem in it is it doesn't work out of the school. And of course, we can have a combination of these possibilities. So you can provide USB dongles for some people, internet authentication for everyone, for example, and you can also have the local server. You can handle all this together. So I'm not going to take longer on the presentation, and I'm going to show you the software live, right? So this is the Open Lab already running. I let it this way just to show you everything before we go through the assembly and every other process. So here you have a brake to work as a load to this motor. This is the torque sensor. Here we have a speed sensor and a stator, rotor, and here some instruments. And you can interact with, like, it's a power supply that sets power to the brake, and the brake become a higher load as I move this potentiometer here. So we can read the current, voltage, and power in different pairs of phases here. And now we can also read the torque meter, the torque in the torque meter, and the speed in the speedometer, right? I'm going to finish and open it again so you can see exactly how it works. Okay. You can stop me at any time, right? Anyone who wants to ask something, feel free to ask me at any time. So this is the software itself. It's got these feature settings, progress, help. Now here we have the topics. I'm going to access induction motor. So we have the theoretical contents here. These are the contents for this specific topic that we are working on, which is the induction motor, right? So if I access the first experiment, then if I'm a student, I'm presented to the experiment, the purpose of it, some basic instructions. I'm told that I'm going to go on 3 steps that are assembly, wiring, measurements, and I can click this button to start the assembly. By doing that, I receive the instructions on which models I need to assemble, which parts, and then I can deliver the assembly when I'm finished. So what I'm going to do is I'm going to do exactly what is required here. So in this experiment, I will need a DC stator with this rotor. Oh, one important thing, when we pass the mouse on a equipment, then we can see what it is. It helps a lot on the process. So let's get the supports. I'm going to finish this thing. Okay, this is better. All right. And now we need to get the models here. I did this so many times that I already know the position. So wattmeter, voltmeter, torque meter, ampering meter, and speedometer. I will leave it out just for you to see what happens if I do something wrong. So let's pretend I am a student and I think I did what was required. Of course, it's not equal. There is one thing missing here, right? And I'm going to place it somewhere else. Okay, so if I try to deliver it, then the software tells me there is something missing. It's a speedometer, and the tachymeter is in the wrong position. So I can solve that by placing the tachymeter correctly and putting the speedometer here. So if I try to deliver it again, then it's saying that something missing yet. It's the flexible joint here and also the brake. And no, I forgot the electronic speed transducer. How could I do that? So let's finish this and now try to deliver again. All right, now we have our assembly perfectly done. Okay, by now we are instructed on how to work on the wiring. So we have the schematic here, and in order to help the student on working on it, we have detailed instructions for each component or each purpose. So let's get to the DC stator. As I said, you can stop me at any time. Feel free to do that. So I'm following the instructions here. Okay. I'll show you what happens if I try to deliver it right now. What happens here is I can see that everything I did up to now is correct, and the white lines mean that there are these things are missing, and the green one means they are correct. So I've finished this first part here. I'm going to go to the brake. I need to connect the brake to the adjustable power supply. Then I need to connect the speedometer with the speed sensor, supply it with 24 volts, and connect the output to the input of the module. Then do the same thing to the torque sensor. Okay. And after that, we need to measure power on the motor. So I don't know that by heart, and I'll need to see how to do that here. So here we got the instructions. Okay, let's go. You connect it to this guy. Okay, wattmeter 1. And now phase 3 with V1, U1 with the amperemeter. I'm curious if I'm doing everything correct. The student could be too. So up to now, I haven't connected anything wrong. So let's keep going. We finished this first part. Let's go to this other one. So phase 2 with amperemeter 2. And here. Okay, let me change the screen so easier. You're here, you go to the voltmeter, and from the voltmeter. Can anyone give me a feedback if you can hear and see what I'm doing? Because I'm receiving some internet connection messages. Help me? Giovanni?
Yes, sir.
Yes, Dennis, there is some a little bit
Hello,
of
everyone.
interruption because you are running the software, I think, so it is a little bit hard to follow everything, talking and making the connection. But it's okay anyhow. We can see everything and we can hear you.
Okay, thank you.
Okay.
I was
Yes,
keep receiving
because the software is running, so it is a little bit, I
internet.
think, yes, for internet connection. But we can see very well. For me, I see very well. If somebody, you can ask the participants if somebody has some problems. Okay. Anyhow, proceed, and we will see.
Thank you.
Okay.
Okay. I think now we have finished. So I should have done something wrong just for you to see, but anyway,
I pressed the validation button, the delivery button, and it's saying everything is correct here. So since I have connected everything correctly, the software run the measurements. It would be good if we had on in the equipments also, right? It would avoid having something damaged by wrong wiring. Okay, so here we have the instruments turned on. I'm going to turn the motor on by turning the 3P voltage on. So now it's running, and I can adjust the load to the voltage using the electromechanical brake. I'm going to turn it power supply on, and now I can adjust the the voltage to the brake, and the brake performs a load to the motor, and we can read the torque and the power and everything else. So in this experiment, particularly, is required to set the voltage on the brake, observing the torque. So he goes from 0, and let's say the first step is placed. Oh, we have it here, I believe. Yeah, it needs to set the torque on these points, then fill the table by reading some measurements from the instruments that are available on the software, and also making some calculations to get some of the information that are here, and they are provided with these formulas to do that. When he finishes it, he clicks the delivery button and delivers. But in the demo version, we don't have this feature. In the real version, the student would see this table come live, and he would fill the table with the data. So this is all that we prepared for this demo presentation, and we are available for your questions and anything else you want to know about the solution. And of course, we are very interested in your feedback as well. Thank you for your time.
Thank you, Dennis.